Okay, so this is lesson 5.6, and today we have 3 vocab words. I had to handwrite them on. So our first one is distance from a point to a line. So that's measured by the length of that's my perpendicular symbol, segment, from the point to the line. So that's our first one. Our next one is equidistant. My last class struggled thinking this was actually equal distance. It's equidistant. And when a point on the same... let's try that again. When a point is the same distance from one line as it is from another line, then it is equidistant from the 2 lines. So when they're the same amount from to the point, that is equidistant. And our last one you've had before, perpendicular bisector, a segment, ray, or line that is perpendicular to our segment and is at its midpoint. So remember, when we bisect something, we split it into 2, and they have congruent measure. So our first one is the Theorem 5.3, angle bisector theorem. In words, if a point is on the bisector of an angle, then it is equidistant from the 2 sides of the angle. Equidistant. So if the point is on the perpendicular, equidistant. It's on the bisector of an angle, then it is equidistant from the 2 sides of the angle. And you see this is we write CB is congruent to BD, because if it is on the bisector, it is the same distance from the sides of the angle. Can I clear the slide? Yes. Our first example is a proof. This one is a fill-in-the-blank proof. So our first part is in the diagram. Ray UW bisects our angle TUV. And angle TUTW and angle UVW are right angles. So you see it already denoted in here. Now we are proving that triangle TWU and triangle VWU are congruent. So our first step, we see that UW, ray UW, bisects our angle. How did you know that? It's given. So first step, it's given. Our second step is, we want to show that 2 angles are congruent because it's been bisected. So what angles bisected, what angles did it form for them to be congruent? So angle TUW, yes, is congruent to VUW. So be careful. Order matters here. So this is our original angle. It has been bisected, which means this angle has been cut in half, which means that TUW and WUV are going to be congruent because it split them into equal measure. And they told us the reason. Definition of an angle bisector. Our next step, the entire step was given. We see that WT and WV, those segments, are congruent by the angle bisector theorem. So the one we just got. So I'm going to draw that in. We see that WT and WV are congruent. Because remember that a point on the bisector is the same distance to each side of the angle. And then our next one is we know that angle UTW and angle UVW are right angles. How did we know that? It's given. Okay, our next one is that angle UTW is congruent to angle UVW. How did we know that? So those are these 2 angles. How do we know these 2 are congruent?
They got the right angle.
Yep, and we know all right angles are congruent because they all have the same measure of 90 degrees. So now we know this portion. How can we prove this triangle? How can we prove that triangle TWU is congruent to VWU? Not exactly. So we can show it by, say it again, AAS. Angle, side. So we know that this one was congruent to this one. So she said AAS, angle, angle, side. When the S is out back, it's the non-included side. So it's the one that's not in the middle. So we have two angles. The side that's not in the middle over here. That's why it's angle, angle, side. Our next step on here is that follow-up question. Write the congruent statements that show how AAS congruence theorem was used. So what angles were congruent and which sides were congruent? So give me 1 second. So what side? TW is congruent to VW or WV. And then which angles are congruent? One is just a one angle letter name and the other one's a three letter name. So angle T is congruent to U. And then we know that angle TUW is congruent to angle VUW. Yep. VUW. Let me fix that V so it doesn't look like a K. Is congruent to VUW. Is it okay if I scroll down? Anybody still writing? Okay. So there we just listed the points that allowed us to prove that theorem. Now we have another theorem, Theorem 5.4, perpendicular bisector theorem. So in words it says, if a point on the perpendicular bisector of a segment is on the perpendicular bisector of a segment, then it is, and what word do you think is going to go in there? Main word of this lesson. Yep, equidistant. And it's equidistant from the endpoints of the segment. So now you see that if it's on that perpendicular bisector, that these are congruent. So the symbols is if C is on the perpendicular bisector of AB, then it is equidistant. We are looking at example 2. Use the diagram to find the distance of AB. So we know that AC is the perpendicular bisector of DB. And we know that AC is perpendicular to DB. And we know that DC is congruent to BC. We see all of that in our photo, right? So the perpendicular bisector tells you, what does it tell us? That they're equidistant from the points, right? Helps if I put the pin on. I wrote from points, and I wrote like this, PTS. Okay, so our first step, since we know that they're equidistant, we know that these two have to be congruent or equal. And so here we know that 8x equals 5x plus 12. So to get this, and we want to get x by itself, what do we have to do? What are we subtracting? We're going to subtract 5x. When we subtract 5x from 8x, what are we left with? So 3x equals 12. Now we need to divide each side by 3, and 12 divided by 3 is? Okay, so our last step is to test your answer to find it because it asks for the distance. So we just substitute 4 in for x. So 8 times 4 is? 32. Our follow-up question is to show that this works the other direction. So you want to make sure that you verified it. So you're going to substitute 4 into that x position there. So you have 5 times 4 is what value, Niqua? 20 plus 12? 32. So did they work out?
Yes.
Yes, they did. Can I switch the slide?
Yes.
Okay. Now we have our first checkpoint on this page. Our first checkpoint, we want to look and find the distance of FH. So, by the theorem we learned today, so by the perpendicular bisector theorem, we know that FH is congruent to HG. So if they're congruent, you know they have the same measure. So now I can just substitute that in. So we have x plus 3 equals 2x plus 1. I want to solve for x. we're going to subtract x. So I get 3 equals 1x plus 1. Subtract 1. What do I get? 2 equals x. I'm not done because the question was to find the distance of FH. We know FH's formula was x plus 3. So we have to substitute in the value of x. So we have 2 plus 3, which is? Okay. So we know based on that perpendicular bisector theorem, yes ma'am? That's an H. Where at the top? 2x? 2x plus 1. 2x plus 1. Okay. So back to the next one. We're using that same information. Based on that perpendicular bisector theorem, we know that LM is congruent to MK, which means that 4x equals x plus 15. So now we have to solve for x. So my first step is to isolate my x. So I've got to combine like terms. How do I get my x to the other side? We're going to subtract it because it's having addition right now. So the inverse of addition is subtraction. So I end up with 3x equals 15. Now and equal, how do I get x by itself? We divide. So 15 divided by 3. Let's go over here. Reggie, what's 15 divided by 3? 5. So our question asks, what is MK? MK equals x plus 15, which means we're going to substitute in x. So MK equals, Alex, you got that one? 15 plus 5 is? Thank you, sir. Okay, now we are looking at our next one, which goes back to that theorem we just learned. So the one regarding the perpendicular bisector theorem. Again, we see that we see that our two sides are also going to be congruent. So we see that FE is congruent to FG, which means that 2x plus 5 equals x plus 10. Do you want to finish solving this on your own? So our next one is we're going to isolate for x. So our first step is?
Subtract x.
Subtract x. We get x plus 5 equals 10. X equals 5. Okay, so we're looking for, yes sir, EF. Yep.
Subtract x, then how is it x plus 5?
So we subtracted x from our right hand side.
Oh,
And so we subtract it from both and just okay. So our formula for EF is 2x plus 5. We're going to substitute in our x. So 2 times 5 plus 5.
15.
Which part?
The EF.
So our goal in this problem was to find the distance of EF. So right now in the diagram, we see that line MN is perpendicular bisector of ST. We want to prove that triangle MST is an isosceles triangle. So our first step, line MN is a perpendicular bisector of ST. How did we know that? It's given. So your first blank is going to be given. Second blank, they told us MS is congruent to MT. So when I put that in my picture, and we know that because of the perpendicular bisector theorem. The last step is that triangle MST is isosceles. What definition told us that?
Bisector theorem.
It's a really good guess. It's the definition of an isosceles triangle. We know that an isosceles triangle has at least 2 congruent sides. So definition of isosceles triangle. Our last one. I'm going to scroll up so you can see the whole thing, okay?
All right.
Okay, so our next one, it says a company plans to build a warehouse that is equally close to each of its 3 stores, A, B, and C. Where should the warehouse be built? So our first step is to draw the triangle and connect A, B, and C. So connect your triangle points. So that is your first step. Our next step is to draw the perpendicular bisector of the segments or the sides of the triangle AB, BC, and CA. Where they intersect, you're going to label it point A. So I'm not going to draw mine all the way up. I'm just going to draw it long enough for it to intersect. And I'm going to give it an approximation because obviously I didn't give you guys a ruler to count this out.
What are you drawing?
Oh, you can't see the green. Okay, it's good to know.
Oh, I see that. I seen it. Where is it? It's real light. It's just got the car.
Okay? So we're going to name that point P.
Oh, is that brown?
Yep. All right. So we draw our perpendicular bisectors and they intersect. So we're going to label point P, and we see that the warehouse should be built at point P because we see the fact that AP equals PB, which equals PC.